In this video, we will use Stoke's theorem to compute a surface integral. So we're given a surface integral of the curl of a vector field f over the surface S, which is the top half of an ellipsoid. Now let's rewrite this equation for the ellipsoid in standard form so we can see what it looks like. So in standard form, the coefficient on the right-hand side is 1, so we'll divide everything by 36. This will give us x squared over 9, which we can write as x over 3 squared. We'll have y squared over 4, so y over 2 squared, and just c squared. So we can tell now from this equation what it looks like. It looks like a sphere stretched by 3 in the x direction, by 2 in the y direction, and not stretched at all in the z direction. And so here's our ellipsoid. This is the top half. And let's remind ourselves briefly what Stoke's theorem says. It says that the surface integral of the curl of a vector field is equal to a line integral of just the vector field itself. And the domain for this line integral is the boundary of the surface S. So in this case, C is what I'm outlining in blue. It's the boundary of this upper half of the ellipsoid. It's the ellipse where it intersects the plane z equals 0. So let's parameterize the curve C before we move on. So you can parameterize it just like a circle with cosine and sine, but use the appropriate constants to stretch it. So it's stretched 3 in the x direction and 2 in the y direction. And this curve C is completely in the xy plane, so the z component is 0. And we'll also want the derivative, because when we evaluate this integral over here, we'll need it for the dr. So r prime is minus 3 sine t, 2 cosine t, 0. Okay. So, since we're told to use Stoke's theorem, that means we shouldn't evaluate the integral we're given. We should instead evaluate the other side of the equation in Stoke's theorem, since they are supposed to be equal. So we will instead do the line integral. So, we should point out first the bounds. T here goes from 0 to 2 pi. And the integral of f along the curve will be the integral from 0 to 2 pi. And now we write the vector field f, but we substitute everything. So for y, we use 2 sine t. And for x squared, we use 3 cosine t squared. So 9 cosine squared of t. And the z component is this big ugly mess, which we're supposed to plug in all of our components from r into x, y, and z. But I'm just going to leave it alone for a second, and you'll see why. Because now we need to do dot dr. And remember, dr is just r prime dt. So we write r prime here. And now here is exactly why I didn't write the big, nasty, messy z component of the vector field f, because we're taking the dot product with a vector that has a 0 in the z component. So whatever this big, nasty thing is, it doesn't matter, we're going to just multiply it by 0. So we might as well not waste our breath writing it all out. Okay, so let's do this dot product. We get minus 6 sine squared of t plus 18 cosine cubed of t plus 0 times the big nasty expression. Okay. So to integrate sine squared, we use the trig identity that sine squared is equal to 1/2 1 minus cosine of 2t. So the integral of 1 will just be 2 pi. The integral here will be 1/2 sine of 2t. But evaluated from 0 to 2 pi, that's just 0. And the trick for integrating cosine cubed is we split it up into cosine squared times cosine. And cosine squared is 1 minus sine squared. So here this first one is just minus 6 pi. And the reason we do this in the second integral is because it allows us to do a u substitution. U is sine t, so du is cosine t dt. So this is just 1 minus u squared du. But now let's think, what are the bounds? When t is 0, u is sine of 0, which is 0. And when t is 2 pi, u is sine of 2 pi, which is also 0. So in fact, this entire integral is just 0, because the two bounds are the same. So our final answer is just minus 6 pi.